I'll make sure sodium's balanced, but because it's not changing, I'm gonna ignore it. If you don't wanna do that, I can do it the other way. So this is the way I would recommend solving the problem. So then I'm gonna break it into the two half reactions. And step one is balance everything but hydrogen and oxygen. So if you left the sodium in there, I would add an Na plus over here. But since I didn't do that, all I've gotta do is put the 2's. The second step says, check the oxidation numbers. This is elemental iodine, this is iodide. So so iodine is going from 0 to -1. It's gaining an electron, but it's doing it twice. So I'll put 2 electrons over here, and I'll check for charge. The left-hand side has a total charge of -2, the right-hand side has a total charge of -2. That's a half reaction. For the other one, the sulfur appears to already be balanced. So I'm gonna go straight to oxidation number. 3 times -2 is -6. It's gotta add to -2, so 2 of these each have to have a +2. So 2 times +2 is +4, -6 is -2. Should I write that out? So 2 times God knows what plus 3 times -2 is -2. So 2x minus 6 is -2, or 2x is 4, or x is 2. On the other side, it's going to be similar. I'm going to say I don't know what sulfur is, but I know that oxygen is -2. Its overall charge is -2. So I'm again going to solve this for x. I got +3 this time. So sulfur's going from +2 to +3. Sulfur is losing an electron, but 2 sulfurs are doing it. So with 2 sulfurs doing it, I'm going to put 2 electrons here. I'm going to balance the oxygens with water. On the left-hand side, I have 3. On the right-hand side, I have 4. So I'm going to add the water. Now I'm going to balance hydrogens with H+. On the left-hand side, I have 2. On the right-hand side, I have none. So I'm going to add 2 H+. And I'm going to add up the overall charge. On the left-hand side, I have -2. On the right-hand side, I have -2. -2 more is -4. +2 is -2. Yay! They're balanced. I find the lowest common multiple of 2 and 2. It's 2. I clap internally. This is oxidation. It's the loss of electrons. So loss always means that they're going to be products that someone else can use. It's going, sorry, this is reduction. This is oxidation. Another way of seeing that fast is that this is going from 2 sulfurs and 3 oxygens to 2 sulfurs and 4 oxygens. We gained an oxygen, so it's going to be oxidation. Shh. Oh, Rashi, I am picture Grace. So cruel. I'm going to add these 2 things together. I'm going to get I2 and water and thiosulfate. Make 2 I minuses and whatever this is, and 2 H pluses. Now to be a good person, I might decide to put the sodiums in, and I would do that in as half-acid a way as I know how. That's the only way I can see to balance them. I still have to have these naked Na pluses. You can imagine that if this was a better experimental procedure kind of thing, if Mohab had been in charge, this is actually salt. And then I could write NaCl here and HCl there. You can see that there's like 2 hanging compounds. There's some anion that they just haven't told me about. Mohab?
Wait, so doesn't the oxidation number go from +2 to +3 for the sulfur?
For the sulfur, it went from +2.
So
So +3, and for the
So-
iodine, the numbers are still there.
Would that make it plus 1 electron?
But there are
Oh,
two
it is.
sulfurs doing it,
Yeah,
so
yeah.
that's where I get the 2 from.
Yeah.
Yes?
So the two electrons that we added, so
Yes.
can you show me how the charges are
So this is neutral, this is -2. This is -2. This is -2 more is -4. But this is +2. So that's a net -2. So both sides have an overall charge of -2. That is for my club. They meet on Fridays. They left the board full of
Improv.
Willy Wonka improv. It's not even improv. Willy Wonka flip the script. Is it?
Oliver tries to.
Thank you, because I feel like I've been looking out like I am no longer impressed. I just see a bunch of freshmaning sometimes.
Is the only time you need to multiply the top and bottom when the electrons are not equal?
That's right, if the electrons are not equal, I need to find the lowest common multiple. Can we do one more of these? We're gonna practice, like, we're gonna do this today, but the ones we have to balance are ones, there's one you haven't seen before. So there's nothing tricky about today, so I planned on practicing one, but if you wanna practice more, this is like opportunity knocking.
So for 16C, I was kind of confused because I was left with uneven charges. So I have like one more electron on the left side and the right side. So in that case, what would I?
So then you would have used the lowest common multiple of the two half reactions to combine them. So I'm gonna do C for free. I apologize if you don't need it. You own this, it's in your file. You just wanna see what the question is, you own it. So, I'm gonna start with the half reactions, because I don't think they're mysterious.
You always start with the half reaction.
Every single time, I break it into half reactions.
So we ever have to find the net ionic equation of the like, did we find the net ionic?
I mean, officially, we did find the net ionic equation, but that's because I didn't know how to handle the sodium gracefully.
So will we ever, are we gonna get questions?
You'll have questions where the potassium and potassium permanganate is included, and you'll have to make a decision as to whether you want to balance it with a K plus or throw it away. That the mark scheme traditionally doesn't care what you do with the potassium, just that you don't fail.
Okay, so I could like do this question like NA at all and like just stop where we.
I think that's how a normal IB question would work. Because typically what we're interested in, what you'll see today, the big question is gonna be, what's the ratio of this to this? And so it doesn't matter if the potassium was remembered or forgotten. And you'll see if you look in the data booklet, I think in table 24, that a number of these reactions are written for you, and they'll never have that spectator ion. So sometimes we can recycle those. Some of you, like Sophia's soon gonna see that there are some patterns here and there are some shortcuts. But like the way I see this, there's a crappy homework assignment you've done. There's gonna be a test coming up in about 2 weeks. There's gonna be a mock exam and there's gonna be a real exam. And so for like 3 times, Sophia's gonna have to demonstrate that she knows how to do this. And so it might just be better to like do it than to figure out the shortcut that makes doing it less awful. So as someone who has written countless answer schemes for this, like sometimes finding the shortcut is convenient, but I'm not going there. So Audrey, if you did this in IGCSE and you're like, I don't mind. Okay. Just like we're doing it in the most orderly way I know how. There are some ways to make it faster, but I don't see a big advantage. So step 1, break it into half reactions. Step 2, balance everything but the O's and H's. S, N, done. Step 3, assign oxidation numbers. Better than me? Any complaints? Step 4, add the electrons. This is an oxidation reaction. Sulfur is losing 2 electrons, 1 sulfur is doing it. This hopefully is a reduction reaction. Arachi's gonna say, of course, you're going from 3 oxygens to 1 oxygen. I knew it was reduction, so I'm glad that that's what I'm getting. Nitrogen is going from 5 to 2. It's gaining 3 electrons. There's only 1. Next step is to balance the oxygens using water. No worries. I need 2 waters on this side. Next step is to balance the hydrogens using H+. Last step is to make sure that the charges make sense. On this side, I have a -2 charge. On this side, I have a -2 charge. The charges on both sides of my oxidation reaction are equal. I'm good. 4 pluses and 3 minuses and 1 more minuses. That's 4 pluses and 4 minuses. That's neutral. That's neutral. Now, Mohab told me that if these 2 numbers of electrons are not equal, that's when I need to do the lowest common multiple. The lowest common multiple of 2 and 3 is 6. I've got to multiply the top reaction by 3. I've got to multiply the bottom reaction by 2. And that's when I add them together. I'm going to get 3 sulfides, 8 H pluses, 2 nitrates, forming 2 nitrogen monoxides, 4 waters, and 3 sulfurs. I check the charge one more time because I make a lot of writing mistakes. This side is completely neutral. This side has 2 minuses, and 6 more minuses is 8 minuses, 8 pluses, it's neutral. I feel okay. Yes?
Wait, so to go back a bit, when you finish the reduction reaction, I have 3 electrons and then 4 hydrogens, and then, okay, wait, and then after that, how did you know to multiply each reaction?
So I'm looking for the lowest common multiple of 2 and 3.
And where do you get?
I multiply them together. 2 times 3 is 6.
So you just choose, like, what do you choose?
What am I choosing? I don't know how to.
Like
The electrons.
The electrons.
Thank you all for hearing that. Thought I had to explain what LCM was, like, I don't know. I know you don't always multiply the numbers together. I know there's some tricks, like 4 and 6, 12, not 24, but I don't know. Better? Las preguntas. So today's class is shorter. You should have time to work on the homework. The homework is practicing your. Ms. Peters shared your mock exam. It's like, it's not a schedule until Friday. It's what she's currently thinking about a mock exam, so that we can have opinions, so that she can give it to you on Friday. She shared that. The preliminary schedule, that's the word I was trying to get, piece. And she actually has you slated to take all of the exams for the classes, which we have not typically done. So that means that you would be taking papers 1, 2, and 3 for biology, chemistry, and physics. Either Myers or Hernandez wrote back and said, we're not ready for a paper 3. And when I was talking to my students in the other section, I was saying my plan was to like erase a couple paper 2 questions and replace them with paper 3 questions. I didn't know that I was gonna have the opportunity to give you a full paper. So I want you to know that it's something that they've given us time for, and I will try to have a decision, but I'm open to feedback. If you took a paper 3, it would be an SL only paper 3. So there's no conceivable way it would be an HL paper. It's gonna be short answer, it's more laboratory and option based. So we start the option 2 weeks from today-ish, and we will study that until the mocks. planned on having a paper 3 test that I could now like pull out of the schedule. But I didn't expect it. We haven't had that in mocks forever. So again, it was like a big surprise, and I'm open to your feedback or criticism or whatever the nice words are, like what you need or want during that time. She thinks it would be beneficial to try a paper 1 and 3 on the same day. That's what the real exam is gonna be.
So for mocks, do we just have, like, the actual exams, you just have one? Well, you said, are we having like one lab, like, all of our chemistry a day, or would we have paper 1 and 2 and then 3 on another day?
I think chemistry is 1 day the way it's set up right now. I'm pretty sure math is 1 day the way it's set up right now, but in the real thing, chemistry would be split across 2 days. In mocks, I know for Quinn's Joy that physics and biology will be on the same day, and so he'll have some moving things around to make that work. Business management and history might be on the same day. I don't know if that affects any of you. So there are some things that are testing at the same, computer science and ESS are at the same time, but you're not in both of those classes, so it's safe.
But is the real IB exam, you're not gonna have just like the same day, like you?
You will, so chemistry is in the afternoon on Thursday and Friday. What's in the morning is anyone's guess, I don't remember. I'm sure Andre doesn't have a test in the morning, but then he figured out like he has psychology and biology on the same day or something. That sounds stressful, and I'm sorry. We'll look it up in a second, so I can either make you stressed or unstress you about that.
I mean, everyone has like a biology day on day.
I'm saying I'm not sure if it's like psych and bio is what sounds right, but I know it affects a number of the people over here.
That's all.
So I'll look it up so that if I'm lying to you, at least it'll be over, and if I'm not lying to you, you can start like stressing now.
Published though, right?
It is absolutely published, I just haven't memorized it.
We can look it up.
Yes, everyone can look it up. I was just trying to start class with something else.
Is there an HL card to this?
1. Sure. I didn't know what it was called.
Me neither, it just said A, and I was like, is this me? I don't know.
Is there an HL part to what we just did?
Yes, so we're still in chapter 9. So you've done 1 day in chapter 9, right? This is day 2 of chapter 9. We're still learning chapter 9. So when I teach Chem Honors, I do balancing redox equations in Chem Honors. I don't know that we'll do it this year, but like in my head, that's something that some of you have seen before. In my heart, I know that's not the case. But in my head, that's why I said if Audrey had done it before, like she could go to town and speed it up. Because I think when I taught Chem Honors 5 years ago, balancing redox equations is something I included in that course. So it is something that people would have come in having seen before. It doesn't mean that they remembered it, but it meant that they would be perhaps seeing some of those tricks. I thought having taken IGCSE, you could have seen it before. Like, it doesn't seem like something that has to be new. But I know for a DT it is new because I know it hasn't been in our curriculum for a long time at Village.
Wait, so we're not gonna do that entire level? That's everything.
Maybe it's teacher. The teacher.
It doesn't smell like teacher.
I think it's a mix. Maybe spearmint.
Here, it's like, no.
Wait, so what do we have to do?
But there's also a
It doesn't smell like syrup. It smells like syrup.
Did you know that spearmint and caraway seeds are optical isomers of each other?
I did not, but now I do.
They are plus and minus carbone. The only thing that's different is the chirality around a single carbon. And that's what takes spearmint and turns it into rye bread.
Rye bread? Spearmint can turn into rye bread.
Caraway seeds.
Oh,
Thanks, Margaret. Where else would you use a caraway seed?
I don't know what caraway seeds are.
That's why I was trying to give you some context. I have let's see if it's right.
Oh.
This is not it. This could be it.
Yeah, it's definitely great.
Okay, this is it. I think this is it. So chemistry is on the 11th and 12th with French. And history. So history, chemistry, French, and chemistry are gonna be in the black box, I hear. Congratulations.
Wait, what? Like, is this a village schedule?
No, this is not the one I wanted, but it is the real schedule. Like, I have one that looks official. This is just what I Googled up.
I have the, yeah, I wrote the original.
French and econ are on a day. Spanish and econ are on a day. Spanish and biology, biology and psychology.
Oh my God.
So bio paper 2, psychology paper 1.
No, but
No, I thought it was 3 SAQs in a year.
I mean, I think it'll be fine.
Do you mind going to May first?
Yeah, 3 SAQs in a year.
Wait, 3 SAQs and what?
And then the
Business
ERQ.
management and nothing.
Not the ERQ was the paper too.
Paper 2 is the
But,
option. Like,
So this is not English, French, or Spanish.
Okay, because on the schedule originally it was like either the first and the second or the third and the fourth. So it's on the third and the fourth line.
Is it?
No,
I was hoping I was.
So it's on the second and the third.
Okay.
Wait, if all of that is the paper 1, then what's a paper 2? So paper 1, so maybe paper 3.
So she put biology and physics on the same day because there wasn't a whole lot of overlap. And biology is a later exam, physics is an earlier exam. So chemistry is going to be quite late. Currently, chemistry is going to be the second week, Wednesday or Thursday of mocks.
We don't know what the paper 3 is.
No, mocks are the last week of February and the beginning of March. And so we will be in the second week of mocks.
Oh.
Right.
Is it too late?
So the first week of March.
Like, I'll
So
relearn all
when
of last year. It's
does
okay.
month ends like the Friday before spring break?
No, you have 1 week of school between mocks and spring break.
We've been doing paperwork for a year and a half.
Everything. Oh, let's do MIT challenge, yes.
What? We have been
I am not in
doing
control of
paperwork
your
for a year.
teachers. I mean, I'm in control of this class, but I can't help what's going on in your psychology class. I don't really have an intention of doing it in this class, so we will never speak those words again, okay?
All that paper two.
Paper 2's
I don't know if we have to or not, Audrey, but I just,
For us, it's
What are we
out.
writing though?
I think it's just.
I'm
Paper three is you get a study and they answer questions.
But we've never seen.
It's like reading comprehension.
That is not good.
Lovely.
Actually, we said, you know what she was, remember when she was in class? She was like, oh, I was probably going to give me all the paper for practice, but I thought that was neat.
She said we're not ready for paper three yet.
Yes,
But it's been 1.5 years.
We kind of are.
We should be ready.
we should be ready.
y'all aren't ready for paper 3 in this class?
We are very.
I know, but you're not, like,
The only time I've taken a real paper 3 was math. They went for a real.
I'm not taking any real paper 3. Is there an English paper 3?
Even bio was a paper 3 that we had.
We had a paper 3?
We've done it.
Oh,
that's the first problem I want you to think
Section B is not
about.
a paper 3. Paper 3 is like the option.
We have typing.
That is only questions are part of paper 2. I thought. What's all?
acid, which is H2C2O4, is a diprotic acid. Beekeepers use it as a solution of this acid as a pesticide. A student carried out a titration with sodium hydroxide solution to determine the mass of the acid in the solution. The students repeated the titration until concordant titers were obtained. What's a concordant titer? In the end of the titration, the two numbers are the same, or they're within 0.1 milliliters of each other. We're getting the same results. We don't believe we've messed up the titration. So there's a balanced chemical reaction that shows that the diprotic acid reacts with 2 units of the monobasic base, which makes sense to me. There are 2 OH minuses to react with the 2 H pluses. And we're making sodium oxalate or sodium, what do we call it? Sodium ethane dioate. I call it oxalate, Audrey. And water. The student found that 25 cubic centimeters of ethane dioic acid solution reacted completely with 25.3 cubic centimeters of 0.5 molar sodium hydroxide solution. Calculate the mass in milligrams of the acid in 25 cubic centimeters of this solution. Are you guys jumping up and down like this is the easiest problem I've seen in forever? This is a normal titration
I don't
process.
remember. Mine's a little blank.
And today's gonna be a tough day for some of you who don't love this. What? Sort of, that's what the titration is doing. It's making sure that we're exactly at the point where we have equal moles of the two things. So, Karthik said, isn't this just like a normal titration? And the answer is yes. To prove that, how could I show you that nothing's being oxidized or reduced? I could just check all the oxidation states. And maybe I could do it in like a low-key way and say I have 2 +1s for the 2 H's and ethane dioate. And I have 2 +1s for the sodiums and ethane dioate, that ain't changing. Sodium's +1 here, +1 there, hydroxide, water. What could possibly be changing oxidation state? This is just an acid-base reaction. All acid-base neutralization reactions are not redox. To solve this problem, you would have done it in topic 1. We don't need to know anything about redox. We don't need to know anything about acids and bases, really. They told us this was diprotic, so we knew it would take 2 of them. All we need to do is some basic stoichiometry. What I mean by that is we're gonna figure out what we can calculate. They told us the amount of sodium hydroxide solution that was used. If they give me a concentration and a volume, what can I figure out? So I want to figure out the moles of sodium hydroxide. It should be equal to the concentration of sodium hydroxide times the volume of sodium hydroxide. Why did I have to move that decimal place? I needed to make sure that it was in decimeters cubed to match. Now that I know the moles of sodium hydroxide, is there a way for me to use a balanced chemical equation to determine the moles of the ethane dioic acid? That's right, there's a 2-to-1 ratio. We know that there are 2 moles of NaOH for every 1 mole of ethane dioic acid. And so if we know how many moles of NaOH there are, we have to divide this by 2, and we can say that the moles of the acid is going to be equal to 0.006325 moles. So, I'm not train tracking a whole lot because I feel like I've train tracked enough that any of you who like train tracking can train track this. I was just trying a different approach. trying to show you what we were getting. The next question it asks is, what is the mass in milligrams of the acid in 25 cubic centimeters? How many cubic centimeters was this moles in? I think it's in 25 cubic centimeters. So this is the right one. So I've just got to take this number of moles and say that 1 mole is 4 times 16 is 64, and 24 is 88, 2 more is 90. This is going to be your whole test.
This problem over and over again.
And so how would I get this into milligrams? I would multiply by 1,000 and tell you that there are 569 mgs of, I'd call it oxalic acid.
Why did they tell us that there's 25 and
Why did they tell you? Well, because in a normal titration, what happens is you make a whole bunch of stock solution and then you do a few titrations against it. And so they're telling you in a particular 25 centimeter cubed aliquot, or like sample of your main solution, this is how the titration went. This is just representing one titer. Often they want to go back to the beginning and figure out what was in that initial big amount. It's on your homework. If it doesn't make sense, it'll make sense shortly. So if we said that the total sample was 250 cubic centimeters, we would say this is to 25 as 10 times this is to 250. So that happened a lot on your topic 1 test,
Right, yeah.
and it happens at least twice in your homework. It seems to be one of those things that we want you to be able to do proportional. Yeah, it seems to come up enough that we should, just practice it a little bit. Okay, so that wasn't hard, I hope. I truly loathe PowerPoint. Is this not how you would solve this problem? Ta-da. Ta-da. Where would you find the answers to this? Where would you find the answers to this? I can't say that in Spanish. I thought I could, but then I started and I was like, yeah. ¿Dónde? Yes. ¿Dónde está las respuestas? I don't speak Spanish. It's no surprise. All of this is on Canvas. So this is called redox titrations. It's in a module called Topic Nom. So if you wanted to see the solution worked out electronically, it's there for you. Okay, so now we have a new one. 24.3 cubic centimeters of some aqueous potassium permanganate solution reacted with 25 cubic centimeters of acidified iron sulfate to form manganese 2. This was taken from a solution originally made in a 250 cubic centimeter flask. I'll just give it a cheat. What was the original mass of iron 2 used? Oh, not even gonna cheat. So how is this the same and how is this different? This seems like a party to me. We care very much about that ratio, but the ratio is not obvious this time. They didn't say, yo, this is a diprotic acid. This time we have to figure out the ratio. How do we figure out the ratio? We have to balance the equation. The equation this time is a redox equation. So we have to think about what the two half reactions are. On one side, we have potassium permanganate. I'm gonna call that permanganate because I've been to this party and I know that the potassium's not doing anything. They told me what the manganese was gonna turn into. What is the oxidation state of manganese in permanganate? It's +7. It's going to +2. Potassium permanganate is a strong oxidizing agent. It's being reduced. It's being reduced by 5 electrons. That means that the iron sulfate, I'm just right out with that sulfate, I'm going straight to the iron, It's a transition metal. They're asking me about iron. I know they have variable oxidation states. I think this is what's changing. What's happening to the iron? Is it being oxidized or reduced? Has to be oxidized, because if something's being reduced, something else has to be oxidized. Iron only has two common oxidation states. They are iron 2 and iron 3. There's actually a table in the data booklet that would help me with that. Most people have done this particular titration. So if you were in SL, they spent like a month doing vitamin iron pill titration with permanganate. I don't know, talk to a friend in that class. Like, that's how they learned how to do an IA. Instead of everyone trying their own thing, they all tried that one. So this is an example of a question that could be in part 1 of paper 3, an experiment I think you might know something about. I believe this is something you might know something about. Why do we love permanganate, Audrey? What does it do that's so magical? When it gets reduced, how do you know it happened? It turns colors. It goes from purple, and if we do it well, it goes all the way to colorless. If we don't do it well, it goes to brown. Fair enough. We'll talk about that in a second. So we are going to use potassium permanganate to oxidize this iron. Let's go. Let's finish balancing this. I'm going to balance the oxygens with water. I'm going to balance the hydrogens with H pluses. I'm going to balance the electrons, and I'm going to be done. To combine these two equations, I need to find the lowest common multiple of 5 and 1. It's 5. I need to multiply this one by 5. If we know that all we're going for is a balanced chemical equation that will tell us whatever the equivalent here is to how many sodium hydroxides react with ethane dioic acid, we were done as soon as we saw this 5-to-1 ratio. Like, that's the piece that we needed to get that proportionality, but I'm going to finish the problem, again, because I have to do this like twice in my life. I might as well just do it right. So to do it right, I'm going to write the full balanced chemical equation. If you look at your homework, you'll see that they just tell you there's a 5-to-1 ratio between iron and permanganate. So if you're looking at not the side where I lovingly chose a few problems for you to do, but you're on the side where they show you how to do this titration, in the 4th box down, it says reacting ratio 5-to-1. Again, this is just supposed to be one that you have a little bit of familiarity with. This reaction is in the data booklet. This reaction is in the data booklet. We didn't actually have to balance either of them. It's just nice practice. We can write them down from table. She's going to tell me if it's 19 or 24. So a lot of these are given. So I would suggest that there's going to be one that you have to balance. But as soon as you knew that the iron had to be oxidized, you could look up that there's only one reaction that's oxidizing iron 2. If you wanted to look up the common oxidation numbers of iron, you could find it. It's going to be 2 or 3 in whatever table that is. I don't know. I feel like I need to spend some quality time with this book, but I don't really enjoy it. That'd be table 14. Okay, is this problem now doable? What would you start by calculating, Sophia?
I don't know.
Think about how we did the other one. So we're going to titrate some of this iron solution with potassium permanganate. What could we calculate about one of those things? What do we have both the concentration and the volume of to get into moles, which is the business of chemistry? Sure, we have both the concentration and the volume of potassium permanganate. So let's use it. Let's multiply those two things together. This one I find really difficult. opposite. I just can't get the zeros right.
I think 0.24.
Oh, but I have to multiply by 0.01.
So, I think I just give me a second.
I'm gonna take 24.30, pardon me, I'm gonna divide by 1,000, I'll multiply by 0.01.
Oh, yeah.
Oh, yeah, that's right.
And now we know how many moles of permanganate we have. Based on the moles of permanganate, is it possible for us to figure out the moles of iron? So there's a 1:5 ratio here, so I've gotta take this number and I've gotta multiply it by 5. So the moles of iron are gonna be 1.215 times 10 to the minus 3 moles. We just took that 1:5 ratio, and I tried to multiply by 5. Yes?
So for problems like this with spectator ions, where we remove the like simplicity here, would it be like problematic if you had an example there where you had to use the molar mass and then you like forgot to add back in the spectator ion?
So if we had to use the molar mass, we would have to worry about that. But what's gonna be your saving grace is gonna be, if the question wasn't what was the original mass of iron 2, if the Amarachi special question was what was the mass of iron sulfate, then all you would do is recognize that there's a 1-to-1 ratio here. So whatever the moles of this is, it's exactly the same as the moles of that. And so you would use the molar mass of all this jazz for your problem. So yes, I think you have to read it, but I don't think you'll get into trouble if you read. If we know how many moles of iron 2 we have, what was the volume that the iron 2 or the iron sulfate was in? Emma's a step ahead, saying that she actually made 250 cubic centimeters, and so she's gonna say that the overall solution had that many moles of iron. So that's that 10-to-1 ratio that we were talking about before. Again, we took a sample and titrated it, but the question is what was originally in that flask. So we multiplied it through by 10. And we want to know the mass, so we're just going to take this number and we're going to multiply it by 55.85 grams is 1 mole. This one didn't ask in milligrams, it didn't ask for anything super complicated, I hope. I got 0.679. How many sig figs have I been, struggling to pay attention to? Because I want to reinforce your math, and I know that unless a problem says, yo, Emma, record this to 2 decimal places, the 3 is always safe. So if the question doesn't tell you what to do, just go with your math, practice your math, get your math points, get these points. I remember Moha when you looked happy in this class.
What if I had multiplied by the mass of the whole instead of doing 10?
So you want to convert this to mass and then multiply by 10? That'd be fine. I'm just saving my calculator to the bitter end because I hate watching people punch on their calculator.
So I understand that we had to multiply by 10, but is that only because it's 25 and 200?
Yes, ma'am.
But then, so what if it's not the same? What if it's like 15 and 200 is the one?
You would multiply by 250 divided by 15.
I lost the And so just really just like March 1, I put it in my calculator, I got 0.677. But I moved to 678. But I did have one.
There's almost always a range of accepted values. It depends on like what molar mass you take for iron, and so the mark schemes are relatively generous.
Okay.
So
Yeah, because I.
Like,
I have 0.8 instead of 55.8.
So I live in fear of a world where you call it 60, and so now you're like out of the thing, so I wouldn't round too much. And 3 kind of prevents you from rounding too much. Come on, little PowerPointiness. I need to put a shape on here, everyone. So yeah, I proved to myself last class that I really don't know anything about Winkler and dissolved oxygen. Also probably proved I don't care a whole lot. I'm gonna try to care more. So measuring dissolved oxygen is a really common use of redoximetric titration. See, for example, my girl. Measuring the oxygen that's in water can tell you a few things. Some amount of oxygen is required in water for stuff to exist, but too much oxygen dissolved in water is a sign that everything's gonna go poorly. So it's a sign of a lot of biological waste. So if you're in a sewage treatment plant, there's gonna be a lot of oxygen in the water because the bacteria are gonna be breaking down sewage and I guess moving oxygen. So the Oxford book gives you some sorts of levels for untreated sewage and by an abattoir. And so now for completion, I need to know if any of you know what an abattoir is.
It's, yeah, French.
Sounds French.
Developed in France.
So your IB chemistry book has words we just don't know. Abattoir, not arbiter. An abattoir is a slaughterhouse, so they give you the value in a slaughterhouse. It's 300 parts per million in a slaughterhouse. I think something under 10 is pretty healthy. It's a lot of parts per million. But one of the poopy things about dissolved oxygen in untreated sewage or otherwise is that it's almost always recorded in the same sets of units. Those units are either going to be milligrams per decimeter cubed, or they're going to know what a decimeter cubed is. What is a decimeter cubed? It's a liter. I heard someone say a liter. How much does a liter of water weigh?
I don't know. It's all conceptual.
1 liter of, how much does a milliliter of water weigh? Okay, how much do 1,000 milliliters of water weigh? A kilogram. A liter weighs a kilogram. You said I'm sorry. So this is a milligram per kilogram. And this is a 10 to the minus 3 over a 10 to the plus 3, which is a 10 to the minus 6. This is a part per million. I don't know how much hint they're going to give you to get to that part per million number. I don't know if the hint is just going to be saying, yo, Emma, give it to me in mgs per decimeter cubed, and looking at that answer and seeing if it makes sense, or if they're just going to expect you to know that this is an equivalence. A milligram per kilogram is a part per million. So hard thing number 1 about this special case of redox reactions is just knowing that it's almost always recorded in units, parts per million, and a part per million is going to be milligrams. What we're going to be looking for is oxygen in liters of water. Water is in quotes because it's not pure water, it's like a water source. Like I'm going to go down to the lake, I'm going to give me a liter of water, how much oxygen is in it? Another tricky thing here is when we talk about dissolved oxygen, we're talking about the molecule you and I are currently breathing. We're talking about O2. We are not talking about O, and we are not talking about the oxygen in H2O. We are talking about dissolved, breathable oxygen. How would this change if we raise the temperature? Would the amount of oxygen go down or up in water? Down. Down. It would stop being dissolved and it would float away. That's kind of counter to what I think salt does, or sugar. If I wanted to put more sugar into water, would I heat up the water or cool it down? I would heat it up. So gases behave a little bit differently, so you just need to think the thought, do I want to open a hot soda?
No.
apparently all of your friends in second period have never in their life opened a hot soda.
No.
Not one of them.
Like a lukewarm soda.
Maybe room temperature soda? It just.
Have you ever left one in the back of your car and had it explode?
No. I don't drink soda.
And then everyone's like, I don't drink soda, so.
Yeah.
Yeah, okay, all you healthy people, like, this is supposed to just be some common sense nonsense, and it turns into, how is it possible you've never done this?
Is that soda?
Yeah, if you'd like some,
No, not like that.
yes, if you'd like some really shite soda, I was doing, have we ever done the crushing a can using the overwhelming pressure in the room experiment? Maybe we can do that. We're not gonna do it right now.
With the contents inside the can?
No, the contents get, so I didn't have enough empty cans, so I went to the store for the second time on Friday to buy the cheapest soda they have at Kroger, which is Citrus Drop Big K. I've never consumed it, but if you need a can of warmish soda, you can have one. Okay, so we're gonna take some river water and we're gonna treat it. Do you see that the way we're treating it looks complicated? Do you think you have to memorize this? You do not have to memorize it, you do not have to balance it, you just have to accept that they're gonna write down a series of 3 equations that you have to look at, stare at, be scared of. They change a little bit. There are a few different schemes for doing this, but ultimately what you're doing is you're taking a manganese compound and you're reacting it with oxygen. If I react something with oxygen, I am oxidizing it. I'm gonna take that oxidized manganese product and I'm gonna react it with iodide. It is going to oxidize the iodide back to iodine. You might recall that if you have iodide and iodine in the same solution, if you add starch, it will turn blue-black.
Yeah, do that for.
Did that for bio and for this class. But thiosulfate can be used to convert all of the I2 that was made back to I- quantitatively. So we could figure out exactly how much iodine was made, which would be related to how much of this manganese got oxidized, which would be related to how much of this oxygen there was by doing a titration using starch and thiosulfate. And so the data is gonna look like, Mohab took some thiosulfate solution and did this titration, comma, how much oxygen was in his water. So step 1, what can we calculate the moles of? What do we have both the concentration and the volume of? Thiosulfate. So let's start with the thiosulfate and say that the moles of thiosulfate are going to be equal to the concentration times the volume. I'm just trying to make these numbers harder and harder for me to see. I get 2.5 times 10 to the minus 5. Is that 6? But Mohab, myself, Quinn, all of us really don't care at all about the thiosulfate. What we care about is the oxygen. And you can see that in yellow, we're showing the path backwards to previous reactions. So what's the thiosulfate reaction? It reacts to iodine that was generated in reaction 2. Could you tell me how much iodine there was? There's a 2-to-1 ratio, so it would be half as much, right? Can you tell me how much of the manganese? So I'm going to multiply this one back by 2. But now here's the one I actually care about. How does this relate to that? And so the moles of oxygen are going to be this divided by 4. It's going to be 6.125 times 10 to the minus 6 moles of O2. I put big parentheses there because I like to go back in time and think about how it happened, but maybe you can see that there's a 2 to 2, so this is a 1 to 1, so I could just replace this with thiosulfate and say there's a 4 to 1. 6.25? You're right, thank you. Totally right. So now that we know how many moles of oxygen there are, we're trying to get it into these goofy parts per million numbers. To get it into the parts per million numbers, I've got to take the moles of oxygen and I've got to convert it to milligrams of oxygen. And I've got to divide it by the total volume of the solution. What is the volume of water that these 6.25, thank you again, Audrey, it's going to make everything better, moles of oxygen in? I don't know how not to railroad track this. Sorry if you hate it. You're welcome if you love it, though. I can get to the milligrams of oxygen first by converting moles to grams and then by converting grams to migs. Decimeters cubed, there are 1,000 centimeters cubed and a decimeter cubed. So if I multiply all of that out, this isn't supposed to be hard. What it is to me is terrifying because it's hard to know what I'm responsible for versus what the problem statement is responsible for. I promise you that the problem statement will always include these steps. 0 times will you be responsible for how to do Winkler. You need to know that Winkler is a method of titrating to determine dissolved oxygen, and you probably should know that equivalence. All of your homework tonight is titration. You're going to start it now or work on your corrections. I will answer questions for all of you, but then for each of you.
So why should you put over 25 water?
Because I want to know how many milligrams of oxygen are dissolved in a liter of water or a decimeter cubed of water. So we knew that we had that many moles of oxygen in our 25 centimeter cubed sample.
But then it said something about, like it said, it required 25 extra of sodium thiols.
So this 25 is this 25. This is the river water.
Okay.
So it's how much oxygen was in that particular sample of river water. But I wanted to know how much would be in a whole decimeter cubed of river water. So that's how I got that last factor of multiplying by 40.
Why are we not doing it over like the water mixed with that solution?
Because we don't care, we want to know what's actually in the river,
Okay.
right? We're not pouring thiosulfate into the river. We want to know how much oxygen was in just the river. So you're thinking about like a titration, what's the pH in the flask after I've added so much sodium hydroxide. So both solutions are mixing there. And like you're completely right that we do that problem differently. But the reasoning that we're ignoring the thiosulfate is because we want to go back to that river and talk about how much oxygen is actually in the river.